Okay, chapter 14. Now that we have stopped or sort of concluded our discussion of states of matter, now we're just going to focus on gases. And one of the properties of gases that make it really unique from liquids and solids is this idea of compressibility. And it's basically a property of gases that the particles can be pushed together. And because of that, you can change the volume of a gas real easily by changing its pressure or by putting it in a smaller container. And you can also manipulate the volume and pressure with temperature. What we're going to look at first is ways that we can affect the pressure of a gas. Remember, in the last chapter, we talked about gas pressure a little bit, and we defined gas pressure is the force of the collisions over the area that the collisions happen over. So basically their container. And in this first example here, we're going to show what happens when to pressure as I increase the number of moles of gas. So if I look in this first picture here, there's a certain number of moles of gas and the pressure is 100 kilopascals, kPa. In the second one, I have pumped down and I have entered more moles or molecules of gas. And so we can see that the relationship is that if I increase the number of moles, I will then increase the pressure. And whenever I ask that, I think about, well, what am I changing? Am I changing the force or am I changing the area? And what I'm changing is I'm increasing the force of those collisions because there's more molecules. Those molecules are colliding with the walls of the container more frequently and increasing the pressure. So the force of the collisions is more. The second way that I can affect the pressure of a gas is by changing the volume. If you look at the scenario here, I have a volume of 1 liter and a certain amount of pressure, 100 kilopascals. When I decrease the volume, I doubled the pressure. So what is the relationship? The relationship is that when I decrease the volume, I increase the pressure. And again, what part of the pressure am I changing? Well, the force is still the same. The number of collisions is still the same, but I have decreased the area that those collisions happen on. And then the third thing that can change the pressure is the temperature. And if I look at the scenario, right, I start with 300 Kelvin and 100 kilopascals. And when I doubled the temperature, look what happened. I doubled the pressure. So what is the relationship? When I increase the temperature, I increase the pressure. Again, what part of the pressure am I changing? The force or the area? And I'm increasing the force, right? Because we know from our discussions last chapter, if I increase the temperature, I increase the kinetic energy of those particles. So that's just an introduction or almost a review of some of the parts of pressure. So now we're going to go into this mathematically. So last chapter we did very little math. This is going to be a lot of math in chapter 14. So the first thing that we're going to do are the gas laws. And your video for one of your videos for this chapter is going to be from one of the gas laws that we look at in this section. So the first one that we look at is Boyle's law. So Boyle's law, look at this diagram. It shows us that the pressure, right? So the pressure in this system is 1 atm and the volume is 10 liters. And then if I push down on the system so that the pressure has doubled, look at what has happened to the volume. It has gone in half. In all of these, notice what's the same. Temperature is the same, right? So this is exactly what we saw in our factors that affect pressure. This is basically as the as when you decrease the volume, you increase the pressure. And mathematically, that is represented by a law that we call Boyle's law, and it is P1V1 equals P2V2. So we are going to do lots of sample problems with this. The first one says a sample of hydrogen has a volume of 473 milliliters at a pressure of 3.56 atm. What will the pressure be if the volume is changed to 250 milliliters, right? Circle the do. What will the pressure be? Underline the clues. I have an original volume and an original pressure, and this is my new volume. Remember what this means. It means the first thing that we always do is we write the formula again. And then I plug in the numbers that I know. My original pressure is 3.56 atm. My original volume is 473 milliliters. The question is asking for my new pressure, and my new volume is 250 decimal point milliliters. You must make sure that the units are going to cancel out on either side. So it really doesn't matter if they're both in milliliters or if they're both in liters. They just need to both be the same answer. And then, of course, algebraically, I would divide both sides by 250 milliliters. Right? The milliliters units are going to cancel out. So my new pressure is going to be 6.74. And again, what unit? Well, every unit crosses out except for the ATM. And as always, we check for significant figures. Every number in this problem has 3 significant figures, so my answer should have 3 significant figures. Okay, question 2 is very similar. So if we were in class, this is the one that I would say for you guys to try on your own. So maybe pause the video, try this one on your own, and then press play again after you have your answer to see how you did. Okay, a 245.6 liter sample of a gas in a balloon has a pressure of 740 millimeters of mercury. What will the new volume of the gas be if the pressure is increased to 876 millimeters of mercury? So P1V1 equals P2V2. My original pressure is 640 millimeters of mercury. My original volume is 245.6 liters. My new pressure is 876 millimeters of mercury, and my new volume is what I want to solve for. So of course I divide both sides by 876 millimeters of mercury. Right, they cancel out, my units cancel out on the left. My new volume is going to be 210 liters, right? Only 2 significant figures in this one because 740 only has 2 significant figures. So that is Boyle's law, volume and pressure. Ooh, that's not what I want to do. There we go. Charles' law. Charles' law is volume and temperature. So look at the picture here. Here's the temperature, here's the volume. I heat up the system so that I double the temperature, and look at what happened to the volume. I doubled the volume here, right? Notice what's the same. The pressure is the same. So in general, Charles' law is when I increase the temperature, I increase the volume, but that's only in we can say like a non-rigid container, but only in a container that has a volume that could change, like a balloon. Often this is done in a balloon. Okay, so a couple things. Now that we're actually going to use temperature in an equation, we need to use absolute temperature. So that means we always need to use Kelvin. And this entire chapter, every time that we use the temperature mathematically, we're going to need to add 273 and turn it into Kelvin. This over here is a graphic that shows those 2 points that I have over here. And this is one of the ways that we've been able to calculate what absolute zero is. Because Absolute zero is what is the temperature when there is literally no temperature, no kinetic energy, no movement of the molecules. Well, that corresponds with zero volume. And you can see where that would be 273, negative 273 right there. So in question 3, a hot air balloon has a volume of 479 liters when the temperature is 15 degrees Celsius. What will the new volume of the balloon be when the temperature of gas is raised to 95? Okay, so first thing we're going to do is we're going to rewrite the formula. V1 over T1 equals V2 over T2. The second thing that we're going to do is we're going to change those temperatures to Kelvin. So I often do this over on the side. So 15 plus 273 equals 288. And 95 plus 273 equals 368. Right? When I'm not really worrying about significant figures when I do this addition, because when I do addition, I worry about decimal places. So it's perfectly fine for me to now count these numbers as having 3 significant figures. So plugging in my numbers, 479 liters happens when the system is at 288 Kelvin, right? What will the new volume be when the system is at, 368 Kelvin? And mathematically, many different algebraic techniques for how to solve this problem. Generally, what I do is I cross multiply here. So then I would wind up with V2 times 288 Kelvin equals 479 liters. 479 liters times 368 Kelvin. And then divide both sides by 288. So the second volume is 612 liters. And again, it's perfectly fine, right? All these numbers here have 3 significant figures, so my answer can have 3 significant figures there. The units of Kelvin are going to cancel out. Again, number 4 is very similar. So if you want, you can pause the video right here at number 4 and try to do this one on your own. Okay, a 4.5 liter balloon of helium gas in a 25 degrees Celsius room. To what temperature does the balloon need to be cooled to so that the volume is decreased to 3.8 liters? So the question's asking about temperature. Again, V1 over T1 equals V2 over T2. The original volume is 4.5 liters. The original temperature, so 25 plus 273 equals 298 Kelvin. The new volume is 3.8 liters, and the new temperature is what the question asks me to find. Again, cross multiply, T2 times 4.5 liters equals 3.8 liters times 298 Kelvin. You don't need to solve this problem the exact same way that I'm doing it with cross multiplication. No matter what you should do, you should be able to get the same answer that I did, which is 251.644 Kelvin. And then again, go look at significant figures, right? This number has 2. We know that the temperature, right? I'm going to convert to Kelvin, and that has 3, and this has 2. So my answer should have 2. So 250 Kelvin it is. The question doesn't say you need to change it back to, Celsius, so you don't need to. Okay, so we've done volume and pressure. We've done volume and temperature. So here's pressure and temperature, Gay-Lussac's law. Look at the picture here. At 150 Kelvin, notice the volume is staying the same this time. And when I double the temperature, I double the pressure, right? So as the temperature increases, the pressure increases, right? And mathematically, here's the formula. Again, always temperature's got to be in Kelvin. So the pressure inside the sealed container is 750 millimeters of mercury at 25 degrees Celsius. To what temperature should the container be changed to in order for the gas to have a pressure of 894 millimeters of mercury? So formula, P1 over T1 equals P2 over T2. The original pressure is 750 decimal point millimeters of mercury. The original temperature, so that is 25 plus 273 or 298 Kelvin. So that's 298 Kelvin. The new pressure is 894 millimeters of mercury, and the new temperature is what I want to solve for, right? Cross multiply, or whatever algebraic technique you want to do, and your new temperature is 355 Kelvin. 3 significant figures here, right? We're always checking our significant figures, but remember temperature, it's okay that it's 25 because we add 273 to it. And the rules for significant figures are different for addition and subtraction. Again, you want to give number 6 a try on your own. Pause the video here and then try number 6. Okay, we'll continue with number 6. A bicycle tire is at a pressure of 3.66 atm at a temperature of 22 degrees Celsius. What pressure will the tire be under if the temperature is increased to 34 degrees Celsius, right? So P1 over T1 equals P2 over T2. The original pressure is 3.66 atm. The original temperature, 22 plus 273 is equal to 295 Kelvin. The new pressure is what I want to solve for, and the new temperature, 34 plus 273 equals 307 Kelvin. Cross multiply, then divide. My new pressure is 3.81 atm. And then okay, I'm like, should we continue? Sure, let's continue. So one more gas law for today, and that's the combined gas law. So if you notice the 3 gas laws that we looked at before, Boyle's, Charles, Galux, here they are in a nice summary of a table. You can see that something is always kept constant. The amount of gas was always kept constant, and in Boyle's law, temperature was kept constant. In Charles' law, pressure was kept constant. In Gay-Lussac's law, volume was kept constant. So what if none of them are constant? And literally, we call this the combined gas law because it combines all of the variables into one. The math for this is exactly the same. Helium gas in a balloon has a pressure of 115 kilopascals, a volume of 75.6 liters, and a temperature of 34 degrees Celsius. What will the new pressure be when the volume is decreased to 52.4 liters and the temperature is decreased to 24 degrees Celsius? Formula. So P1 V1 over T1. Have you noticed temperature is always in the denominator? My original pressure is 115 kilopascals, kPa. My original volume is 75.6 liters. My original temperature is 34 plus 273, or 307 Kelvin. My new pressure is what I want to solve for, so P2 is there. My new volume is 52.4 liters. My new temperature is 24 plus 273, or 297 Kelvin. Okay, so how do I do this? Well, like again, there's many different algebraic ways to solve this problem. you can cross multiply. That's how I do all of these. I just find that I make less mistakes when I cross multiply. But you know that there's lots of different ways to solve these problems algebraically. But cross multiplying gets rid of the fraction, which is where students, if they're going to make a mistake, they make a mistake. And then you would divide both sides by the product of 52.4 times 307. And your new pressure is going to wind up being 161 kilopascals, right? Every number in this problem has 3 significant figures again, right? This guy is 3, and this guy is 3, and this guy is 3, and my temperatures are always 3. Number 8, the final problem today is the exact same type of problem, so feel free to, again, pause it, try this problem on your own, and then check your work. A volume of xenon is held at a temperature of 32 degrees Celsius, 5.7 liters, and 775 millimeters of mercury. What will the new volume be if the pressure is dropped to 600 millimeters of mercury and the temperature is dropped to 0 degrees Celsius? So P1 V1 over T1 equals P2 V2 over T2. My original pressure, 775 millimeters of mercury. My original volume is 300. That's not true at all. It's not 305 Kelvin. My original volume, 5.7 liters. My original temperature, this is going to be 32 plus 273 or 305 Kelvin. That goes in the denominator over here. My new pressure is 600 decimal point millimeters of mercury. Remember that decimal point means those zeros are significant. There's my new volume that I want to solve for. And my new temperature, it's 0 plus 273, which is, of course, 273 Kelvin. Again, cross multiply, do whatever algebra you need to do, but your new volume should come out to be 6.6 liters, right? 2 significant figures because 5.7 is only 2 significant figures. Every other number in this problem has 3 significant figures. Okay, so those are the 3 different gas laws, and then the combined gas law, which literally combines all 3 of these together. Your homework, the homework problems that correspond to these are numbers 33 through 43. It's just a continuation of the numbering from the last chapter. Okay, so try these, ask any questions in the instructional review sessions, and good luck.